Hello, fellow PyMC enthusiasts. My name is Abuzar Mahmood, and I'm a postdoctoral fellow at the Taste Dynamics Lab at Brandeis. And today I'm really excited to share some of my work using probabilistic change point models to study neural dynamics related to taste processing. And I'll be giving a talk in a few more days, followed by a Q&A, where I'll give the context for this work, basically what I study, what are these states in the brain that we're trying to detect using change point models, and what do they represent, why we're so interested in them. And even why that, talking about why these change point models are the appropriate types of models to use to answer the questions that we're asking. I'll also briefly go over the theory behind finite and infinite mixtures, because that theoretical knowledge will be useful for some of the model building that we'll be doing. But all of that will come later. My goal for this video is to essentially go over these models together with you and discuss their inner workings. So let's dive right in. The layout of the talk is as follows. We'll briefly go over the data we'll be working with and visualize it, after which we will discuss three different types of models. The first one of these, which I call the simple Poisson multivariate change point model, is the one that will kind of really dive into the guts of and figure out all the nitty-gritty details. And once we have a foundation for how these kinds of models work, we will be extending this simple, quote unquote, simple model in two different ways, which address the limitations of the simple model. The first of these, the Dirichlet process change point model, will attempt to automatically infer the appropriate number of states or change points present in the data, whereas the mixture emissions model will attempt to explicitly account for inhomogeneity or drift in the emission rates present in the data across subsequent observations. And with that, let's dive right in. So this notebook, if you'd like, you can run it in Colab. I'll be running it on my computer, but it's been tested to work on Colab as well. To kind of give you some context for where these data come from, in my line of work, we do a lot of what's called extracellular electrophysiology, which means that we stick a wire into the brain and we record activity outside neuronal bodies. And whenever a neuron is active, it generates these very sharp voltage deflections around it, which we call spikes. And for many neurons, if you deliver a stimulus, to the animal, you can see that many neurons respond with a reliable pattern of activity. In other words, following a stimulus, many neurons show a reliable pattern of spikes in time. So let's say I give sugar water to a rat, then I would expect some neurons in the brain to show a specific pattern of spiking activity. And so to be able to better visualize the spiking activity instead of looking at these very noisy raw voltage traces, we basically extract the timings of these spikes to generate a binary time vector where a 1 would indicate every time that neuron spiked. And these are what we call spike trains. And analyzing the dynamics of these spike trains can inform us about which brain regions are active in response to a stimulus, when they get active relative to the timing of the stimulus. And for my work, I use the information present in these spike trains to try and study what the dynamics of brain region interaction are in response to a taste that is delivered. But while these spike trains showed here are at a temporal resolution of 1 millisecond, to kind of make our modeling, our model fitting run a little faster, I have binned these kind of data into 50 millisecond bins. And for the kind of neurons that we work with in my lab, even 50 millisecond binning doesn't really destroy the dynamics the temporal dynamics that we see in the activity of these neurons, but it will speed up our model fitting significantly. So to be more concrete, we will load data from an extracellular recording from the gustatory cortex. And if you're interested about more details on where these data come from and what are other ways they can be used, I would highly encourage you to look up this paper. But these recordings, in the recording that we'll be dealing with, involves 30 repeated deliveries of a single taste, what I will be calling 30 trials. We recorded from 7 neurons simultaneously, and we have 4,000 millisecond of spike trains for every trial. And I've binned these into 100 millisecond bins, so we'll have a total of 40 time bins. So my apologies, I said previously that the binning was 50 milliseconds, it's actually 100 milliseconds. And we'll see that even with that, we'll be able to see significant dynamics present in the activities of these neurons. So we load the data from a NumPy array, and we can see that's a 3D array that's trials times neurons times time. For the first 2 models I'll show you here, I will be summing the total number of spikes across trials. This will give us an on average view of the activity of the neuron. While generally in my lab, we tend to stick to single trial analyses, so we will fit model to all 30 trials individually to, again, for illustrative purposes and to save some time, I will just be focused. I'll be taking this as a single trial example. And then for the last model, we will actually use all 30 trials because the phenomenon that we're trying to model is actually an across trial phenomenon. So once we sum these spikes, we are left with a 2D array that is simply neurons times time. And we'll visualize both the original data and the sum data. Looking at the original data, we have our 7 neurons where each plot is a different neuron. Trial number is on the y-axis and time is on the x-axis. And the brightness of the color indicates how many spikes this neuron was firing in each given time bin. And we'll notice that all of these neurons not only show changes in their activity over time, that is along the x-axis, we can also see that the patterns of activity change across trials along the y-axis. Specifically, if we look at neuron 3, we can see that in the first half of this recording, this neuron seems to be firing much higher than it does at than during the second half of this recording. And this kind of behavior, this both temporal and across trial, across time and across trial changes, are what we will model using the mixture emissions. So to start with our first model, we will be building a Poisson multivariate change point. I call it multivariate because we're modeling the activity of all 7 neurons at the same time. Excuse me. And this example borrows very heavily from Cam Davison-Pilin's probabilistic programming and Bayesian methods for hackers, which I think is a phenomenal introduction to Bayesian modeling. If you're new to Bayesian modeling or PyMC, I would highly recommend this. And the example you'll see, if you've already gone through this book, you'll see it's very similar to the change point example they use in there. So looking at our summed activity, we have neuron number on the y-axis and time on the x-axis. And again, the dynamics that we saw in the individual trial data are even more strongly highlighted here. We can roughly see, if you had to decide, you'll probably say that there's about 3 states in here, one with a change point around 10 and the other around 30. And so how do we actually go about modeling this multivariate time series? We'll first start with just taking some parameters. So we'll extract the number of neurons and the number of time bins, which is what we'll need to model the firing rates. The emission rates, I will use emission rates and firing rates interchangeably throughout this talk. But essentially what we'll try to model is the latent emission rates for every time bin for each of these neurons. We will set the number of states to 3 for now, and this is just selected based on domain knowledge. A lot of previous work has shown that the activity during this time period consists of 3 states. We kind of just eyeballed it 2, and 3 states seem to agree reasonably well, so we'll go with that for now. And then when we go on to the Dirichlet process change point, we'll get more validation for this specific selection. And then we're just creating an index vector, excuse me, that runs through all that marks the time for the whole data set. And this will be used in building the model later on. I always like to provide some initialization values for the lambdas. And so here we're just generating a mean firing for the data equally split into as many states as we dictated. So here we've set 3 states. So if we split the data time-wise into 3 sections and take the average emissions for that, for those chunks, we will be using our initial values as those average firing rates for the data divided evenly along time. So to create this model, we'll basically need 2 latent parts. The first of them is we will need to know the emissions for every neuron in every state. So thinking about it from the perspective of if we had to represent this data as sequential states, to be able to do that, we need 2 parts. One is knowing when the state transitions happen, so when one state goes to the next, and the other would be what is the firing rate or the emission rate of each neuron during every state. So for the emission part, because we're dealing with count data here, we want a distribution that is discrete and is positive. And we could either use the Poisson or the negative binomial here. The Poisson has 1 less parameter, so let's go with that. And to be able to calculate a Poisson likelihood, we need the emission rate for each data point that we're giving it. So if you're familiar with the Poisson distribution, we'll need a lambda variable for each data point that we're giving it. The lambda variable has to be positive and continuous. And we can have a lot of different distributions that fit this criteria. But again, for simplicity, we will use the exponential distribution, which again has just 1 parameter. So we instantiate our lambda latent, the emission rates for each state that we're trying to infer. We provided the initial values that we calculated, and the shape is number of neurons times number of states. So again, for every state, we will need to know the activity or the emission rate for every neuron. And the prior parameter for that, the prior mean for that is 0.1. And I have some plots further down, which will explain why I'm using 0.1 as a prior here. But for now, we go on to the next piece that we need to construct this model, which is the change point position. Now, we're trying to model this data. If you're trying to model state changes over time, one way we can go about it is basically take the duration of the data as a 0 to 1 interval, right? And if we can say that a change point happens, if we say any number on that 0 to 1 interval marks how much time has passed as a fraction, given the duration of our data, we can always scale it up to match the actual values for our time, for our n time bins. So basically, if we can say that, let's say there's a change point at 0.3 on a 0 to 1 scale, we can always scale it up to our 40 time bins. So it would be 0.3 times 40. If you've gone through Cam Davis and Palin's book, you'll see that in the example for the change point there, they're using a discrete time. But one of the reasons we would want to use continuous time is so we could actually use a nut sampler instead of a metropolis sampler. And so using a continuous distribution instead of a discrete one would be beneficial for when we're actually trying to perform our inference. So that means that we want a distribution that is, one, continuous, and here we're trying to model the values on an interval from 0 to 1. And a beta distribution fits these exact specifications. So we instantiate our tau latent, which is our change point locations on an interval from 0 to 1. We choose 1, 1 as the distribution's prior parameters. And for a beta distribution, giving it a 1, 1 will basically give you a flat prior. So equal probability of the change point occurring anywhere from 0 to 1. We initialize the distribution using what I call even change point locations. So this will, for 3 states, we will have 2 change points. And so this bit of code here will basically give us 0.33 and 0.66 for our initial values. And as I said before, for the shape, we want states -1. So for 3 states, we want 2 change points. An important thing that I will note here is that to make sure that each change point is identifiable, we will have to sort the beta variables that come out of this. So in our case, our 2 change points, we want to make sure the change point 2 always follows change point 1. And so we sort these variables. So one is always greater than the other. If we don't do this, what might happen is, in some cases, change point 1 might come before change point 2. In other cases, it might come after. And that'll create problems with not only inference, but also identifiability. And so once we have our tau latent, we actually do the task of scaling it up to the interval of the length of our data. And here we use the index vector that we created above to basically scale tau latent from an interval of 0 to 1 to an interval of 0 to 40. Okay, so with that, we have the building blocks of what we need to create this model. We have both the latent variables defined that we would need to be able to generate a time series that looks like this. But now we actually have to do the task of putting our latent variables together to be able to generate this kind of time series. Essentially saying where a state starts and ends and what values, what emission variables are present during that state. And again, if you've looked at the example in the Bayesian Hackers book, you'll see that they use the switch function to say when a state ends and the other begins. That kind of discretization, again, will prevent sampling using nuts. So instead of marking states using the switch function, instead we will use sigmoids multiplied together to mark timings where a state is prominent. And to visually show you what this looks like, I've graphed out some sigmoids that are multiplied together in the appropriate fashion to be able to generate states. So at the bottom here, we have 3 different sigmoids. Let me change the color of the last one. Or not. We'll just stick to the first two, and then we'll get rid of the third one for now. But basically what we're doing here to generate this red line up here above is we're taking f and multiplying it with the inverse of g. So we basically flip g upside down and we multiply f with it. And that gives us this kind of bump that demarcates where these states are happening. And the onset and the offset of these states is given by the inflection point of these sigmoids. So basically our change points would be the inflection points of these sigmoids. And we can construct these states in this specific way by multiplying the sigmoids together. And, excuse me, and then we can go on to use this state as an indicator variable and multiply our emissions with it to generate the time series that we want. And to be able to do this for a 2D array, I create basically the analog to the forward-facing sigmoid, which I call the forward stack, and the analog to the flipped sigmoid, which I call the inverse stack here. And to just visualize what these look like, the forward stack here has these sigmoids which are going from 0 to 1, whereas the inverse stack here has these sigmoids going in the opposite direction. And both the forward stack and the inverse stack have these states which are just 1 without a sigmoid. And that's because at the ends of the time series, you only have a sigmoid going from either 0 to 1 or from 1 to 0. We will only have states generated by multiplication of sigmoids in the middle, but at the states at the edges will only have one sigmoid. And so when we multiply the forward and the inverse stack together, we can see that for the 0th and the last state, we only have a sigmoid facing in one direction, whereas the middle state comes out to be a multiplication, a product of these sigmoids. And when we actually perform this multiplication to generate the weight stack, we get an array that is of shape states times time. And I will remind you that the lambda latent, our latent emissions that we generated above, are of shape neurons times states. So to assign essentially the emission rate of a single neuron to a single state, we can take a dot product between these two arrays. And we'll use the tensor dot function present in the PyTensor library that comes with PyMC. And we will tell it that for lambda latent, we want to multiply the first dimension, which here is states, with the 0th dimension for weight stack, which again is states. And what will come out of this is an array with the shape neurons times time, which corresponds exactly to the shape of our data. And hence this would complete the generative process of creating an array that that corresponds to our estimate of the underlying firing rates present in our count data. So again, visually representing that here. So once we have our final weight stack, we take the dot product of that with our lambda latent, which is neurons times state. And each cell here represents the emission rate for a given neuron for a given state. And once this dot product occurs, we get what I'm calling just plain lambda for the rate of the Poisson likelihood. And you can see that for different states, these lambda latents have been appropriately assigned to different states over time. Great. So we just write in the likelihood or Poisson likelihood with the lambda as the rate and the sum spikes as our observed variables. And before we finally press the magic inference button, I mentioned that I'm going to go over why we picked the hyperparameters for our priors the way we did. So for lambda latent, I had put 0.1 as our hyperparameter for the mean rate. And again, this was just by trial and error. We can see that when we sample from the prior, our lambda latent values go from 0 to about 40. And if we go back to our actual data, we see that it has a range from 0 to 25. So this means that for a mean value of 0.1, our exponential prior here appropriately represents the different values that are the different potential rates that this data could be being generated from. And another quick visualization is simply just looking at the ordering of the taus. So the necessity of that sorting step that was present in our tau latent here is so that we have values where tau 1 is always smaller than tau 2. And so just one final visualization for this model. We have our two pieces, the change points and the actual emission variables, and we put them together into a rate array that serves as the generating rates for our count process. And we finally go on to press the inference button, and we see that our traces look pretty nice in this case. There don't seem to be any divergences or any other warnings. And so now that we fit our model, let's see what we can get out of it. We'll generate some plots of the actual data with the inferred change points overlaid just to visualize how well it seems to be working, looking at the posterior predictive observation to get more insight into what the model is seeing, how the model is generating this data. We want to look at the distribution of change points. For me, using the uncertainty in the estimation of the change points is very important, because especially when I'm working with sparse data or neurons with very low firing rates, hence low counts at the time series that I'm using, the uncertainty in the estimation can work as a very important filter and very important kind of qualifier to judge kind of how valid is the inference, how valid are the inferences that I'm doing, or how confident should I be in the answer I'm getting, in the answers I'm getting from these kind of analyses. And then finally, just looking at the inferred lambda rates. So when we plot the mean inferred change points and overlaid with our data, we can visually see that it agrees with what we would have expected, that there is one change point somewhere between 5 and 10, and the other one is somewhere around 30. And looking at the mean posterior predictive, we see that it very strongly resembles the actual data. And so that suggests to us that we're probably not missing anything significant in the actual data, that our model is actually capturing a good amount of variance present in the actual data. And in this case, our change point, inferred change point distributions are very tight. We're very confident about where these change points are happening, which again agrees well with the fact that we were able to look at this and just kind of say where the change points should be happening. And then finally, we're looking at the inferred emission rates for each of the states, the lambda latents. And it goes from 0 to 16, which agrees by and large of what we would have expected just by looking at the data. Great. I think this is a good point to take a little break, and then we will move on from here to adding more components to our quote-unquote simple model to address specific limitations of the simple model and try to address specific limitations of the simple model. Welcome back to the second part of the talk. In the previous section, we went over the Poisson multivariate changepoint model. And if you remember, as we were defining the model, we explicitly gave it the number of states as a model parameter. Now, this parameter, I said we fix using domain knowledge, or we just kind of eyeball the data and we're like, yep, this looks good. But at the end of the day, the model will not be able to give us any information about 2 states or 4 states. And there are many instances where we just don't know how many states or how many change points should be. Or in many cases, we are, especially for me, I'm trying to use the model to tell me how many states should be present in the data. And one method to figure out the number of components in many models, and this could be anything like hidden Markov models, change points, k-means, clustering models, is to use model comparison metrics. And while I've used things like AIC, BIC, or ELBO in the past for inferring number of change points, if you want to actually see the specific example I'm talking about, I've put a link here to my previous paper, which uses these model comparison metrics. What I've always found lacking is the interpretability in the values that these metrics return. So, for example, if the AIC is telling me that the 3-state model is the best and the 4-state is the second best, the actual values, the difference between those values, is dependent on the data given to it. And so it's hard to compare how much poorer the 4-state model is compared to the 3-state one. And so to improve this interpretability, what I would really like is if the model told me the distribution over the number of components. And here we employ a Dirichlet process prior over the number of states to give us something similar to that. And this code borrows heavily from code that's already published for the Dirichlet process mixture model up on PyMC examples. And if you'd like to see how this model behaves using some very clean simulated data as a test case, I've also linked to some additional reading, a blog post that I've written using this model. But one of the things that is very important to me in this case is being able to get the estimate of the uncertainty for the number of states. For the previous model, the data that we used was summed across all of the trials, and that gave us very crisp, clean-looking data where the inference from the model, the inference of the change point locations was very strong. So for the specific model, we were very sure where the change points are. And because we were sure where the change points are, that might even boost our confidence about how many change points there are. But for this specific example, I wanted the data to be more realistic. So instead of summing across all 30 trials, I just summed across the 7. I just summed across the first 7 trials. And so the data that we get out of there, out of that summation is plotted here. And we can see that there's still, we can still see roughly 3 states, could even be 2 states, we're not quite sure. But I didn't want to go all the way to single trial examples, just so, but have something in between that's somewhat easy to look at, but also not completely crisp. So as we begin defining the model, I'll go over the exact instantiation of the Dirichlet process that we're using. The Dirichlet process comes in many flavors. The one we're using is called the stick breaking construction. There's also the Chinese restaurant process and the Polyas-Earn process. And as opposed to the stick breaking process, the Chinese restaurant process will actually give us a discrete distribution over the number of change points that are being used. But here we're using the stick breaking construction for its ease. And the way this construction works is that a Dirichlet process is a set of infinite samples where you can take each sample to be the length or the fraction of a stick of size 1. So if for the stick breaking construction, if we were actually able to keep track of an infinite number of values, we would have a set of infinite fractions of this stick that sums to 1. And the thing that determines how big each chunk or each break of the stick would be is a parameter called alpha. And the higher the alpha, as shown in these examples here, the more pieces we get, and the smaller the pieces are, where the y-axis tells us the length of each piece. Whereas if alpha is smaller, then we have fewer pieces, but they're all larger, and the number of pieces is given by k. So alpha determines how big each break is, and depending on how many breaks we want, we will sample that many beta variables, and the beta will determine how big each break is, and each subsequent beta will keep telling us what fraction of the stick that is left over should we break again. And this wonderful picture here was actually from one of Thomas Wickie's papers. So if you need a more in-depth explanation of how the Dirichlet process works, I would refer you to this manuscript. Another note that I'd like to make here is, as I mentioned in reference to the Chinese restaurant process, that the stick breaking representation does not explicitly model state counts. Instead, it simply tries to fit the appropriate number of states. So what we'll be using technically in this instance is what's called the truncated stick breaking representation, because we cannot actually keep track of an infinite number of values. We set the number of components to a high maximum. So in our case, if we're expecting 3 to 4 states, we'll maybe set it to 15 or 30. But basically you want to set the maximum to a place where you're sure it will capture the number of components that you roughly expect. And what the model will do then is use these fractions of the stick as weights for your model. So if it's a mixture model, it would be the weights of each of the components. In this case, we'll be using each of the fraction as the duration of each of the states. But that means that we will get a value for each of the states. Sometimes it could be very close to 0, but sometimes it doesn't. Other times it doesn't have to be. And that means that to actually get something similar to the number of states or the number of change points present in the model, we will have to do some thresholding at the end. And I'll refer back to this when we actually get to that point. So actually converting this into code, this stick breaking, the code for this stick breaking function is simply this equation converted into code. And again, I've borrowed this from the Dirichlet process mixture code from PyMC examples. And then we start building our model, again, starting with parameters, the neuron numbers, the number of time bins, creating our index vector, and setting our maximum states. So in this case, instead of 15, we set our max states to 10. We could set it to 15 too. It'll just increase the computational cost a bit. And similar to our previous example, we're just taking the prior of our Poisson rate, the lambda latent, as an exponential variable. We're still dealing with count data, so our likelihood is Poisson. And so the rate variable has to be positive and continuous. So an exponential distribution fits the bill again. Moving on to the actual change from the previous model is finding or creating the generative process for the location of the change point variables. So each time series that we'll be modeling is divided into chunks or states using the Dirichlet process, which here we're instantiating using the stick breaking process. So the alpha variable that we see here above that dictates how big each break of the stick has to be, or how big each break of the stick should be, and therefore also how many breaks we will have. We're instantiating that using a gamma variable, and then the rest of it is simply putting the stick breaking process into action, where we have a beta distribution such that its parameters are 1 and alpha, and then we feed the beta into the stick breaking process, which will return to us the fractions of the stick indicated by these alpha and beta. And once we have our stick lengths, what we want to do, again, because this is not an infinite process, it's a truncated process, what we want to do is make sure that all of our lengths add to 1. And so we do some normalization here to get our W latent, or our latent weights, where the weight is actually the length of the state. And to get our tau, we simply sum all of our W latents multiplied by the time bins. So W latents are fractions, which will add up to 1. If we multiply that by the time bins, it will be state lengths. And then when we sum them all together, we will get the endpoints of each of the states, which will be our change points. And once we have defined the generative processes for both our lambda latent and our change point variables, the rest of the process is largely the same. We generate our weight stack, which is created by multiplying sigmoids together to denote our states. And then again, we simply take a dot product between our latent emissions, or lambda latent, with the weight stack to obtain our lambda, which is our instantaneous rates underlying the count data that we see. And we feed it into our Poisson likelihood. And just to see a few more examples of how the alpha and the alphas and the betas work, in our specific case, I've drawn samples from the prior. So here we see that for our alpha, we set a mean of about 10 and standard deviation of 4. Right? But importantly, what these alpha values return to us are W latents, which I'll remind you are the fractional state durations that we obtain from the stick breaking process. This using this distribution of alphas gives us fractions which go from 0 all the way to 0.6. So we're spanning quite a bit from having the possibility of very small states to very large states. And when we take the cumulative sum of these state durations, this is what we get, that for going from 0 to 10 states, sometimes we increment in small steps, so the states are rather short. In other cases, if you can see this, we start out at a state that is as large as 0.7, and then small increments take us all the way up to 1. Great. So just visualizing the graph for this particular model, starting out again with alpha, generating our betas and feeding that into the stick breaking constructor, from which we use a cumulative sum to get our taus. And once we have our taus, the rest of the process is the same. We just mix it with the lambda to obtain our instantaneous firing rate. One thing I will, which is probably pretty self-evident here, is that the sampling setup is very different from how it was for the simple Poisson model. And the reason for that is that with this specific model, the sampler seems to get stuck very easily at a single value of beta. We will actually make plots of the traces later on, but to remedy that, we're running a lot of chains and then using the variability in the chains as a indication of the uncertainty present in our inference. Another way to do this would be to use sequential Monte Carlo sampling. The way I've written it the specific way is simply because I haven't figured out the parallelization in SMC just yet. So this works well for me for now. So once we've performed our inference, we make plots for the inferred state durations. Again, looking at the raw data and comparing it to the change point locations. And going back to our discussion in the beginning, I mentioned that because the stick breaking construction doesn't necessarily give us discrete values for the number of states present in the data, to obtain an idea of how many states are present, what we actually have to do is threshold the fractional durations or the state durations that we get from this Dirichlet process to say something about how many states are probably present in the data. So the first of these plots is simply the sorted number of states inferred by all of our chains. We can see that the first state usually runs from like 0.5 to 0.7. And the second one is roughly about 0.25, 0.3 in length. And succeeding states get increasingly smaller. And this threshold of 0.1, for now, it's set somewhat arbitrarily. The idea being that if a state is less than 10% of the total time, then it's probably not worth calling it a state by itself. So if we see states larger than that, let's take those and let's count them as full-fledged states. So if we compare our tau samples to the actual data, we see that the bumps in the tau distribution correspond roughly to where our previous simple Poisson model found the change points, somewhere between 5 to 10, and then somewhere close to 30. So ultimately, the inference of the change point location is very similar to what we saw in our previous example. But what we expect to be getting on top of that is actually how many states are present in the data. So to visualize these inferred state durations in a different manner, here I've plotted the sorted latent W, the latent W again being the fractional state duration, from the model. And we see from our 50 chains that the largest state can be as large as somewhere 0.8. And generally, if we go by the weight of these states, there could be perhaps 3 states present in the data. And if we're thresholding at a level of 0.1, then it seems like there is a tie between the model saying there are 2 states or there are 3 states. And when we look at the data, we can kind of see that if, similar to our previous modeling example, if we put a change point here and another here, then we'll have 3 states. That seems to describe the data pretty well. But if we go with the larger bump and just stick a single change point around 10, that, I could see there being only 2 states present too. But this plot is essentially what I was going for when I was constructing this model, is the inference being able to tell me how comparable different number of states are for the given data set. However, this analysis assumes a fixed threshold, right? And one way to get a better idea, or to get a more holistic idea about the stability of this analysis that we've done here, is to look at how the number of states changes if we change the threshold. And so if we just repeat the same analysis for thresholds, in this case from 0.1, 0.01 to 0.2, and create that distribution, we see that as we increase the threshold size, the number of states change very quickly. And so that's likely not the solution because it's not very stable. But as we approach 0.6 and then 0.1, it seems to very consistently show that there are 3 or 2 states present in the data. Then what we can do is collapse all of this across one dimension to get a histogram that gives us these state counts across all thresholds. And again, we can see that largely it's the inference is suggesting that we have 2 states, and 3 states is a close second. Right. At this point, we'll take a second break before we go on to our third and final model, which will explore modeling changes in the stability of the emissions over time and try to address drift and inhomogeneity in sequential observations. All right, welcome back to the third and final installment of this tutorial video. In the first section, we discussed using a Poisson multivariate change point model to infer change points in neural spiking data. Then we went on to extend the simple model to try and automatically infer the number of states that are present in the data that we're dealing with. However, both of these data sets use trial average data. And because we were literally summing the activity of neurons across trials. Now, this assumes that this activity stays the same. In other words, it assumes that the mean is a good summary statistic or a good representation of the actual data. Or put another way, averaging across trials, as we have done above, assumes that the data do not drift. And while this is true in most cases, in many cases I encountered personally, data for all the trials do not come from the same distribution. And as a specific example, I'll refer you to this manuscript, which shows that within multiple sets of trials, the pattern of spike trains seems to flip-flop between 2 components or two different patterns. And so in such cases, we need to account for the inhomogeneity present across trials and treat these sets of trials differently. Otherwise, our model will likely perform very poorly. And as an example, on dummy data, if you'd like to see what happens to inference when we fail to account for inhomogeneity, I will refer you to this blog post done using this specific model. And so this the solution to this problem would be easy if we knew which trials were different. We could just take them out or fit different models to each set of trials. But in many cases, we don't have any a priori knowledge about which trials come from one set versus which from the other. Another reason we might want to fit a model to all the trials collectively is to improve inferential power. As is true for actual data, in this case, we're assuming that the position of change points does not necessarily change from one trial to the next. However, the emission rates do. And so keeping all trials together while accounting for differences in emissions will increase our inferential power for figuring out where the change points are. And so a principled way to address this issue is to use a change point model which also allows changes in emissions. And one way to do this would be to use a model that allows for a mixture of emissions. And so if the model has more than one set of emissions it can use, then it can probably, if let's say the system drifts from one set of emissions to the next, then the model can simply scale the emissions across different trials between these two sets of emissions. And again, in the model below, we assume that the change point positions do not drift. So having a look at our data to see, to remind us what this drift looks like. Again, if we look at neuron 3, we see that the first 15 trials look pretty different from the latter 15 trials. Similarly for neuron 5, in the latter half of this recording, or the latter half of this data set, this neuron seems to be firing much more highly than in the first half. And so roughly, trials after number 15 exhibit different emission rates than those before. And so this means that if we fit a change point models for multiple trials, it would be foolish to assume constant emissions. But before we actually get to putting this model together, I'd like to briefly introduce the Dirichlet distribution, which we'll be using to model the weights of each of the mixture components. So as opposed to the Dirichlet process in the previous example, the Dirichlet distribution is finite, and it will simply return us a vector of values that will all sum up to 1. And basically the magnitude of each of these values is determined by this alpha parameter, where generally the larger alpha is, so let's say in this vector, in this bottom right example, alpha is 2, 4, 8. Then we would expect that the first value this distribution would return is the smallest, the second one would be larger, and the third one even larger. And so this is a principled way to obtain vectors which we can use as weights because they will always sum up to 1. All right, now moving on to actually defining the model. Again, starting with our basic parameters. This time we also have to keep track of the number of trials. So previously we were using single trial data, or what we artificially constructed to be single trial data. But now, because we're observing a change across trials, we also need to model emission rates for multiple trials. We're, however, back to hard coding the number of states across time. And now we're also setting the number of components that we want for the mixture distribution of emissions. And ideally, both of these would also be automatically determined, as in the previous Dirichlet process example. But given the amount of data versus the degrees of freedom in the model, that might not always be possible. So because this will tend to be a somewhat large model, again, I would like to start it off at a good point for the lambda latent for the latent emissions. And so we're calculating our initial values, again, by chopping across both time evenly and across trials evenly. And just averaging between those evenly divided chunks. And so first, to build a model, we'll first start by defining the mixture weights. We will define this as a marginalized mixture, such that we are not categorically assigning observations to the clusters. And a similar example would be to look at the differences between a Gaussian mixture model where we're explicitly modeling what cluster the data point comes from versus a marginalized Gaussian mixture model, an example of which I've given here. And similar to this marginalized Gaussian mixture model, we will be using a Dirichlet distribution, which has, again, repeating what I mentioned above, which has finite dimensions, hence not to be confused with the infinite dimensional Dirichlet process above. And this distribution will provide us weights that will sum up to 1. So the parameters, the concentration parameters of this distribution, this set of alpha vectors here, we'll define that first, and then we will define our weights as coming from this Dirichlet distribution with hyperparameters being these alpha w's. And our weights will be of shape number of trials times number of components. Essentially, what we want to get is for every trial, what is the weight of each of the mixture components for the emissions. And so hence we will need a shape that's number of trials times number of components. Then moving on to the latent emissions, the output of the latent emissions in this case would be pretty much the same. But here, because we've added another dimension, where we're dealing with a sparser and larger data set. Again, I'll remind you, previously we were summing spike counts across multiple trials. And so, let's see. So when we sum across all trials, we get this very clear data showing very obvious dynamics. And then for our next example, we used a smaller subset of data. We summed across a smaller number of trials, and we can see that these dynamics are looking sparser and sparser. And then you can imagine that as we end up on single trials, here, for example, neuron 0 only fires in 3 different time bins. And so dealing with this larger yet sparser data set means that we have a much larger degree of freedom. So we would need to define lambda for all the neurons, for both components, and for all the states that were given. And so in order to basically constrain this problem more, we're hierarchically defining the lambda to reduce the independence of the final lambda latent. And so the idea is that the reason we can do this is that we're essentially asserting, but it's by and large true, that all the activity of a single neuron is more similar to itself than to the activity of other neurons. And so if we basically initially define what I'm calling neuron lambda, which, let's say, it's the mean activity, it's an estimate of the mean activity of the neuron. Then if we define trial lambda, which would be the emission rate of every neuron in every trial, and we inherit the hyperparameter of that from neuron lambda, that will be a much better estimate of the trial lambda than if we were to assume that all trials are independent from one another. And similarly, if we take that one step further and we try to infer the emission rate for every neuron, for every state, for both components, then being able to inherit that hyperparameter from neuron lambda, then from child lambda, will provide us a better estimate than assuming that all of these different values are independent from each other. So it provides a sort of shrinkage and constraint to the inference problem. Following that, the change point position definition is largely the same. Now we're also using a hyperprior over tau latent, again, to provide a constraint across multiple trials. So this is assuming that the hyperprior across all trials is the same, even though the change point positions across multiple trials may be different. So previously, our tau latent was a single vector because we only had one trial, but now our tau latent is a 2D array with shape trials and states -1, so number of change points. And so we're providing a constraint by enforcing the fact that the hyperprior over the position of the change points is the same across all trials. And then again, simply scaling it to the actual length of our data. And then we move on to generating our weight stack, which in principle is the same, but now we have to deal with an additional dimension. And I won't go into the details of that too much here. You're welcome to play with the code and then look at the different shapes and how they come together. But the idea is essentially the same, that now instead of wanting a weight stack that is simply states times time, we need to add the additional dimension for trials, because the position of the change points will change from one trial to the next. Excuse me. Finally, as we start to put all of these things together, we need to determine from our mixture weights and the actual latent lambdas what the emission rates will be on a specific trial. And here I'm calling that selected lambdas. And we're basically doing another dot product between W, which, let's see if I can do that here. So W is shape trials times components. Oops. So this is trials times components, and state lambda is neurons, components, and states. Shapes neurons times components times states. And so what we want out of our selected lambdas is something that tells us for every trial, for every neuron, for every state, what is the emission value. And performing this dot product will basically multiply across the component dimension and return to us an array that is of shape trials, neurons, and states. And then finally, multiplying our selected lambdas with the weight stack, where we have to do some additional massaging of these particular arrays, because our selected lambdas is of shape trials, neurons, and state, whereas our weight stack is of shape trial, state, and time. And what we want to end up with is an array that is of shape trials, neurons, and time. So essentially, we need to get rid of the state dimension in both of the arrays that we're multiplying. So we reshape selected lambdas to a shape that is trials, states, and neurons. And we reshape weight stack using dim shuffle. We reshape both of them using dim shuffle into trials times state And then we have our simplex dimension that we'll use for broadcasting, and then time. And so when we multiply both of these together, we will end up with, put this here, trials times n states times neurons times time, right? And then we simply sum across the first dimension to get rid of it, and we're left with an array that is trials and neurons in time. And then once we have our final lambda for spanning all the same dimensions as original data, we can feed it into our Poisson likelihood to finish the model. And so here is a summary picture of the model. Let's see if I can open it into, no. There we go. So slightly more complicated than the previous models we made, but essentially all of these emissions can be collapsed into one facet of the model. These taus can be collapsed into a second. The specific addition that we've made, as opposed to compared to the simple Poisson model, is adding this alpha W and then adding multiple components to, or multiple sets to the emissions that we assign to each trial, and we scale and assign to each trial using the weights derived from the Dirichlet distribution. Right. Once we've put that all together, we perform our inference. And here I'm using the NumPy sampler, using the JAX capability added to PyMC, which greatly speeds up our inference. And once we have our samples, we will generate plots for the mixture weights across trials to, basically try to visualize whether it agrees with our initial assessment of how these changes were happening in the data as we saw it. And we'll plot the inferred latent emission components. We'll plot the z-scored state lambda across trials to highlight changes. Sorry, so one of these should be we will look at the state lambda across trials, and then we'll also z-score it and plot it to basically highlight the changes happening across trials. We'll also look at the change point positions across trials and compare the actual data to the mean posterior predictive to see how well it resembles the actual data. So plotting the mixture components across trials, we see that in the early part of the trial, the two mixtures roughly account, by and large, for are roughly weighted equally. And then a sudden and dramatic change happens between trials 10 to 15, where one of the mixture components becomes significantly more dominant than the other. And so initially, it seemed like the model was taking an average between the two sets of mixtures. And then it decided to use, by and large, one of the emission sets to generate the data. And so if we look at state lambda across different trials, where each column is a different neuron. So first, we're looking at changes happening across different trials, where the top row are the actual emissions for each of the 7 neurons across trials, and the bottom row shows the z-scored emissions. And we can see again around trial 15, there's a big change happens. Some neurons show a unilateral increase in their activity across all states. Other neurons show just a blanket decrease in their activity. Only 2 neurons show nuanced changes, where For some states, there is an increase in inactivity. For other states, there's a decrease. For neuron 1 and for neuron 2, first state, let's say the 0th state shows an increase, and the first and second state shows a decrease in its activity. Looking at the chain point positions, it doesn't give us too much information. We can see that roughly changes seem to be happening around somewhere between time points 5 to 10 for the first change point, and for the second one, somewhere around, let's say, 30 to 35. And then finally, looking at the posterior predictive observations compared to the actual data, you can see that by and large, they do capture the dynamics present in the data. If we look at neuron 3, for example, the posterior predictive accurately shows that the first few trials, this neuron is firing much higher in the earlier parts of the trial than during the same time points in the latter parts of the trial. And for neuron 6 and for neuron 5 as well, we can see changes happening around trial 15. And so I don't do a thorough comparison of what breaks if we don't do this kind of explicit modeling of changes in the emission variables, but I would like to refer you to my blog post here to see basically a case study. If not, it's not really a systematic analysis, but a simple case study of how much better the emission model performs on inhomogeneous data compared to a model that simply assumes that the emission stays constant across trials. All right. Thank you for bearing with me. I hope that description, those explanations were helpful. To wrap up, I would like to acknowledge my thanks to my PhD and postdoctoral advisor, Dr. Donald Katz, under whose mentorship all of this modeling work was done. I'd like to thank Dr. Narendra Mukherjee, who was the first person to introduce me to Bayesian modeling, and specifically to PyMC3. I'd like to thank my funding sources, grants to Don from the NIH, and postdoctoral fellowship from the Swartz Foundation. All of these models were created and heavily influenced using open source code shared by PyMC developers and users. And so I'm grateful to everyone for sharing the work they've done. A special thanks to the PyMC organizers for giving me the opportunity to share my work, and especially to Raveen and Purna for their advice and coordination on the back end of putting this event together. Thank you, everyone.